researchers started to question everything, from disk evolution and migration mechanics to the influence of stellar winds and magnetic fields. Perhaps there were unseen processes at work, violent gravitational encounters early in a system's life that could fling planets inward or outward in chaotic dances. One alternative theory proposed that the planet formed from a localized gravitational instability, collapsing rapidly from a clump of gas without the need for a solid core. This process, while theoretically possible, had never been observed, and certainly not at such close proximity to a star. Some began to suspect that these types of planets weren't as rare as we once thought. Maybe we had missed them before, hidden in the glare of their parent stars. With better telescopes and more sensitive instruments, they were now being revealed, one anomaly after another. This forced astronomers to confront an uncomfortable possibility: that our models were too simplistic, too Earth-centric, too reliant on the few dozen well-studied planets of our own solar system. The universe, as it turns out, doesn't care about our categories. And this wasn't just about one strange planet. Other worlds were starting to challenge expectations as well. Super-Earths, planets larger than Earth but smaller than Neptune, were being discovered in abundance. Yet our own solar system had none. Hot Neptunes and lava worlds, tidally locked exoplanets with one side permanently facing their star, creating temperatures that could melt metal. Each new class of exoplanet added another crack in the framework we once believed was solid. In the wake of these discoveries, entire textbooks had to be rewritten, simulations updated. Students and scientists alike had to adopt a new mindset, one that embraced the bizarre, the unexplainable, and the outright contradictory. This wasn't just a scientific evolution, it was a philosophical one. What do we do when nature refuses to behave? In science, we're taught to observe, to hypothesize, to test. But what happens when the observations produce outcomes that no existing hypothesis can explain? Some began to wonder if the problem wasn't the data, but the lens through which we were interpreting it. Could it be that we were projecting our assumptions, our sense of order, of symmetry, of logic, onto a universe that is inherently asymmetrical, chaotic, and unpredictable? After all, we've only known about planets outside our solar system for a few decades. In cosmic terms, we're barely out of infancy. Maybe these strange, impossible worlds aren't the exception. Maybe they're the rule. And maybe it's time we stop trying to force the universe into a framework of understanding that was never meant to contain it. The impossible planet taught us that sometimes, to move forward, we have to break what we thought was unbreakable. Not just theories, but paradigms. The science wasn't broken. Our confidence in its completeness was, and that may be the most exciting discovery of all. The impossible planet wasn't alone. As telescopes became more powerful and data collection more precise, a curious pattern emerged. One anomaly could be dismissed, a fluke, a statistical outlier. But 2, 5, dozens? That was something else entirely. We began to see worlds that made no sense according to our models. Planets that orbited not 1, but 3 stars. Rogue planets drifting through interstellar space, unattached to any solar system, moving silently and invisibly in the dark. Planets that appeared too old to exist in their current state, or too young to have reached their apparent size and complexity. Take, for example, PSR B1620-26b, nicknamed the Methuselah planet. It orbits a pulsar and a white dwarf and is estimated to be over 12 billion years old. That's nearly 3 times older than Earth, and formed not long after the universe itself was born. And yet, there it is. Or HD 106906b, a planet that orbits its star at a staggering 650 astronomical units, a distance so vast it defies explanation. How could it form so far away? Why didn't it escape the star's gravity entirely? Then there are ultra-short period planets, massive gas giants that orbit their stars in less than a day. These worlds are so close to their suns that they are being stripped of their atmospheres in real time, vaporizing as we observe them. And yet they remain stable long enough to be seen, measured, and studied. These aren't science fiction, they're science fact. And they're telling us that the universe is not just stranger than we imagine, it may be stranger than we can imagine. What's becoming increasingly clear is that planetary systems are far more diverse than the tidy clockwork arrangement of our own solar system. Our 9 planets, now 8, follow relatively circular orbits, lie in the same plane, and move in the same direction. This seemed normal until we realized it was actually the exception. Other systems are chaotic, tilted, misaligned. Planets get ejected, stars swallow their own offspring, moons become planets, and planets become moons. Migration is common, violence is routine. Cosmic order? It's an illusion built on the limited view we had from our own backyard. And while we were trying to understand how things should be, the universe kept showing us how things really are. These exceptions matter because they challenge the very nature of science. Science thrives on predictability, on the ability to model, forecast, and explain. But when you encounter system after system that refuses to conform, you must either cling to outdated models or build new ones that are flexible, dynamic, and open to chaos. And chaos, as it turns out, may be the most fundamental law of all. Some scientists now believe that our solar system's neatness is the result of countless near catastrophes, stabilized by sheer cosmic luck. Maybe Jupiter prevented more extinctions than we realize. Maybe Earth's position, just right for life, is not common, but precarious. Which raises another question. If so many planets shouldn't exist by our standards, how many others are out there, escaping our detection entirely because they don't fit the patterns we expect to find? We might be looking for planets in the wrong places, using the wrong criteria. We're hunting Earth-like worlds. But maybe the most common planets out there look nothing like Earth. And maybe, just maybe, some of them don't even follow the same rules. In embracing the cosmic exceptions, we also begin to stretch the boundaries of what life might look like. Planets with exotic chemistries, subsurface oceans warmed by tidal flexing, atmospheres thick with gases we once thought toxic, but which, in another context, could support unfamiliar life. The impossible planet was the spark. But the fire it lit has revealed a universe filled with wild, unexplainable, magnificent diversity. If the laws of nature are being rewritten, then so too is the story of what's possible. With the accumulation of anomalies, astronomers began to ask the hardest question in science. What if our foundational theories are wrong, or at least incomplete? When one planet defies expectation, we question the planet. When hundreds do, we begin to question the framework itself. In doing so, we open the door to alternative explanations, some rooted in physics, others drifting toward the philosophical. One of the most provocative ideas is the simulation hypothesis. First popularized by philosopher Nick Bostrom, it suggests that all of reality, everything we see, feel, and measure, might be an advanced simulation running on computational power beyond anything we can imagine.